the Moivre's theorem. And you actually know it already. That's the cool thing about it. Because what Moivre did was really formalised what we already know. And that is, if I raise a complex number to the power of n, the argument gets multiplied by n. Remember that idea? We said the argument of z to the power of n was n times arg z. And that's exactly what Moivre's theorem is saying here. Now, his theorem just says for all integers n, turns out it doesn't have to be an integer. It works for negative numbers as well. It works for fractional powers. It works for all of them. Now, it's a bit more useful if we include modulus as well. And remember the added bit we know, that when we raise a complex number to the power of n, the modulus gets raised to the power of n. So that's a little bit more useful because the first one, the Moivre's one, is assuming the modulus is 1, of course. But the modulus could be anything. So if I want to find 1 minus I to the power of 5, yes, I could expand the whole thing out. And power of 5, yeah, okay, that's probably not that much work. Imagine if the power was something like 23 or 24. You know, that's going to take you a while to write all the terms out. So Moivre's theorem can be very handy for this, because what we do is we change the 1 minus I into mod arg form, and the modulus of 1 minus I is the square root of 2. The argument is minus pi on 4, because the real part's positive, the imaginary part's negative. So we were looking at a negative acute angle there. So we now know it's the square root of 2 cis minus pi on 4 to the power of 5. So all I have to do is raise the square root of 2 to the power of 5 and then multiply the argument. So the answer is the square root of 2 to the power of 5 cis minus 5 pi on 4. Now, depending on how we write the answer. If they want the answer in mod arg form, then I'm going to change this argument. Because remember, we said we want our arguments between pi and minus 5 pi on 4 is not. If I was going to return to Cartesian coordinates, I wouldn't worry about it, because I'm going to say the cos of that angle anyway, the sine of that angle. So if we were going back to, if we were staying with polar coordinates or mod arg form, then the angle would become 3 pi on 4. And root 2 to the power of 5, of course, is 4 root 2. If we were going to go to Cartesian coordinates, then I can say, all right, remember, cis stands for cos plus I sine. So the cos of 3 pi on 4 plus I sine of 3 pi on 4. So the cos, well, that would be negative, 1 on root 2. Sine would be positive 1 on root 2. Multiplying out, and there's our answer, minus 4 plus 4i. So a lot quicker than expanding the whole thing out. Because remember, after we would have expanded the whole thing out, we then would have said things like, oh, hang on, but I squared is negative 1. We'd have to sort all that out. Then we'd have to collect like terms. And so a little bit quicker. And it's great if the angle turns out to be an exact value, or one that we know. Because otherwise, hang on before I move on to this, otherwise, if it's not one that we know, say it turned out the argument was, 22 degrees. We don't have an exact value for that. So we'd end up with an approximation using Moivre's theorem. All right, finding roots then. Now we've talked about finding the square root, but of course there are many other roots. There's cube roots and fourth roots and fifth roots and sixth roots, and I could keep going on. Moivre's theorem is really useful for this. Okay. So z to the power of n is equal to some complex number, and we want to work out what z is. Well, I change it to mod arg form. So z to the power of n becomes r cis theta. And z then would become r cis theta to the power of 1 on n. Remember, Moivre said whole numbers, but I told you that actually it does work for fractions as well. And so if it's to the power of 1 on n, then the modulus goes to the power of 1 on n, so the nth root of r. And the argument we divide by n, because we'd say theta times 1 on n. But there are going to be multiple answers. Remember I talked about that rotation around the circle. And so we just substitute in values for k. So we go 2 pi k, because 2 pi is just one trip around the circle. So I'm back at the same place. If I go around 360 degrees, I'm back at the same place. So I can add on 360 or 2 pi as many times as I like, and I'm at the same place. and we're going to divide it by n, and we just keep substituting in consecutive numbers. Usually we start at 0. Doesn't have to, just has to be consecutive numbers. Some people like to start with a negative number, and then you can create conjugates by sort of making it symmetric. So, say there was 5, it was the power of 5. Instead of going from 0 to 5, they'll go from -2 to +2 and use symmetry, so they end up with conjugates straight away. So it doesn't matter, just consecutive numbers. All right, let's try it. So a simple one, z squared. We talked about finding the square root, but now we've got another way of finding the square root. Because we can say, well, z squared is 4i. 4i, if I put it in mod arg form, is 4 cis pi on 2. Okay. So z, well, the square root of 4 is 2. So I know the modulus. And then for the argument, I add 2 pi k, because I can go round the circle, many times as I like. I'm in the same spot. And then divide it all by, well, in this case 2, because we're finding the square root. And I've chosen to substitute in 0 and 1. Okay. If I substitute in 0, I get 2 cis pi on 4. Substitute in 1, I get 2 cis 5 pi on 4. And those ones are exact values, so I can calculate them out. And tidying that up, there we go. There's my answers. The root 2 plus root 2i and minus root 2 minus root 2i. Another way of thinking about it, again, using the idea that we're evenly spaced. As soon as you find the first answer, then you got the rest of them. Yeah. So I could have said, well, I know the first answer's there, 2 cis pi on 4. I know there's 2 answers in my circle. Therefore, the next answer must be how far around? Yeah, 180 degrees or pi. So my other answer must be over here. And if I add pi to that argument, I'd get, well, I wouldn't get minus 3 pi on 4. If I add pi, I'd get 5 pi on 4. But converting that into an angle between pi and minus pi, I get minus 3 pi on 4. So I can use that knowledge about, okay, they've got to be evenly spaced. So once I know the first one, I can just look at my diagram and say, oh, well, I know they've got to be this far apart. Let's do a fourth root. So the fourth root of 16 we're basically finding here. Well, 16, and I know it looks a bit silly right in mod arg form, but it would be 16 cis 0. So my answer will be the fourth root of 16, which is 2. 0 plus 2 pi on k. Well, that's just 2 pi on k. This time I'm dividing by 4. And I've chosen to start at 0 and go 0, 1, 2, 3. So my 4 answers, 2 cis 0, 2 cis pi on 2, 2 cis pi, 2 cis 3 pi on 2, which would be 2, 2i, minus 2, and minus 2i. If I was doing it the other way, this is where the rotation idea is really cool, because fourth root of 16, I don't even need to go into mod arg form. What's the fourth root of 16? 2. It should have been a little bit quicker because we'd already worked it out there, by the way. So because that turns out to be a real number, I can plot the 2 and then say, well, I know they're evenly spaced. There's 4 of them in a circle. Therefore, they must be every 90 degrees. So now I've got one there, and one down there. There's my 4 answers. Whee. Okay, let's have a go at playing with this Moivre's idea.